Hello and welcome to the Geodict AI breakout session. As I also already mentioned yesterday, my name is Rolf Westerteiger. I'm a senior software developer at Math2Market, and AI is one of the components that I work on, mostly together with Andreas Grieser. And today I want to show you how you can use Geodict AI to train your own neural network model for different to be used in different modules within Geodict. The agenda looks as follows. I will give a short overview. Then I will explain to you how the FiberFind AI workflow works. And then I will talk about the aspect of extracting the fibers, which works using semantic segmentation with deep learning. Then I will talk about the so-called digital statistical twin, and how you can use the digital statistical twin to then create training data to train your own neural network. And finally, I will show you how to apply it to your own materials to analyze them. So as an overview, Geodict uses neural networks for segmentation and object identification, amongst other functionality. Geodict 2024 ships with some pre-trained models for fiber identification and binder segmentation, which already give a good result for a wide range of materials, especially with the new improved FiberFind model that we ship. But if your materials are outside of the scope of these pre-trained models, outside of the distribution that was assumed when training those models, or if you want to get even better results, you can train your own model using the Geodict structure generators and using Geodict AI, as I will show you in this presentation. And this has now become easier than ever. And I will show you how to train your neural network optimized to analyze your specific materials. And this training procedure usually only takes on the order of days on consumer GPUs. As another option, as Andreas Wiegmann mentioned earlier, the training and inference can also be run in the cloud if you don't want to invest into this GPU hardware yourself. Within this breakout session, you will learn how Geodict AI and FiberFind AI work under the hood, and how you can train your own optimized models. And for this presentation, we will be using fiber identification as an example, but most of the workflow is the same, for example, for material phase segmentation, for example, binder identification, and also for image enhancement. And within this presentation, we're going to have two breaks of about 15 minutes each. And please feel free to ask questions at any time during the session. And for this purpose, please raise your hand and take the microphone so the online participants can also hear you. So first of all, let's formulate the problem of fiber identification. Assume, for example, that you have a segmented micro-CT image of a non-woven material sample. So we have a binarized image. We assume we have a micro-CT image. We have segmented this with traditional means, so import GeoVol, for example, with an ODSU segmentation. So now we have a binarized image where we have two material phases. We have the void space, so the matrix material or maybe air, and we have the fibers, which is the other material phase. And each voxel exactly belongs to one of these two phases. Again, we use a non-woven as an example here, which consists of long curved fibers with a constant diameter. And our desired output in the very end is to have a statistical characterization of our material sample with, for example, fiber curvature, fiber lengths, diameter distribution, which identifies and characterizes our material, which allows us to compare the material, for example, against other materials. But many of these statistics cannot or can only be computed on a complicated way directly on the voxel image. So what we want to do is we want to obtain an analytical representation of the fibers. We want to know where the fibers are and how their trajectory is through space in order to be able to analyze all these high-level statistics easily. Now let's talk about how FiberFind does this. In the first step in FiberFind AI, we take again the binarized image as an input, the segmented micro-CT image. And the first step produces a segmented image where the center lines, as we call them, are marked. So the center lines are about is a trajectory and at the core of the fiber, which has a diameter of roughly 2 to 3 voxels, which is marked as an additional material phase, as you can see here in the right-hand image. Let me see if I can get the pointer mode here. Yeah, okay. As you can see here on the right-hand side, Here I have visualized the image and I have cropped away the red material up to this point and this point, so you can see how these added trajectories, these center lines, continue through the fibers. And you can see here again, here's a cross-section view with a pseudo-SEM depth view, as you can see, where you can see that the core of the fibers, these center lines, has been marked by FiberFind AI. And this is the first step in the process of extracting an analytical fiber representation. And how this exactly works will be a focus of this talk, but I will first continue describing the rest of the workflow. In the second step, after these center lines have been extracted, there's a post-processing step. First of all, and this image does not convey that at this point, but first of all, these center lines are reduced to curves of a diameter of roughly 1 voxel, which is called skeletonization, which many people know. It's an image processing. Algorithm. Skeletonization reduces these center lines to a diameter of about 1 voxel, and the resulting curves are then traced to obtain analytical fiber trajectories. And based on this representation of these traced fiber trajectories, we can observe that sometimes a couple of defects can occur. Like you can see here, there is a crossing between two fibers. The center line was fragmented. So if we were to take this representation as is, we would obtain 4 fiber fragments at this point, even though we have actually 2 fibers which are crossing each other. So there's a post-processing step which is hard-coded in GeoDict, specifically for fibers, which will, for example, remove short isolated fragments and will bridge these kind of gaps between fiber fragments before the next step starts. In the next steps, then we will produce GUT data. GUT data, those seasoned GeoDict users will probably know what that means. That is the analytical object data. So basically in GeoDict, we have 2 types of representations. If you generate a fiber structure, for example, with FiberGeo, you will have both an voxel image, which is the obvious thing that you can see, but you also have an analytical representation of the fibers, which is called the GUT information. And you can see that on the left-hand side, there's a green icon on the left-hand side if you have that GUT information for your data set. And if you have that GUT information, then you can do something like this. It's a bit small, this image. On the upper left corner, you can actually click. You can actually click on a fiber that you have and select it as an object. And this clearly tells you that GeoDict knows that this is an object and it's not just a voxel image. On the right-hand side, you can see another representation of this. This is a so-called G32 file, which you can generate anytime you have GUT information. You can generate that directly from within GeoDict, which shows different objects in a different color. So basically, this is a label image where each integer label identifies a certain fiber, and all voxels belonging to that fiber have that same label. And there's a colorful visualization of that to make you to enable you to see the individual fibers. So starting from the first step, the post-process and repaired center lines are then analyzed. They are simplified to piecewise linear polylines. So we have basically straight segments representing a chain of short straight segments representing each fiber. And then in order to extract the diameter of that fiber, we use the Euclidean distance map. Some people might have had contact with that in GeoDict because it's used in other modules as well. For example, in PoroDict for pore size analysis. The Euclidean distance map gives you in this case, for each voxel within a solid phase, it will give you the Euclidean distance to the background, to the void space, basically. So if you were to sample this Euclidean distance map at the very center of a fiber, you would ideally get the radius of the fiber at that point. And because the center line is centered within the fiber, we just trace that center line and we sample the Euclidean distance map versus the void space at each of these points. And we basically get a function of the fiber diameter along the fiber trajectory. And from that, we then approximate a local fiber diameter. And I believe we store this for each of these, basically for each of these polyline points, we store this local fiber diameter. And so the resulting data, which is those polylines, so basically the points along the fiber connected by straight segments, plus the radius or diameter information that we have at each point, is sufficient to construct a GUT representation of these fiber objects. So basically, what we have at this point is, from its nature, identical to what an output of FiberGeo looks like. It's the generator that would generate a fiber structure. So, and last but not least, and the last step, of course, then knowing the trajectories of all these fibers, knowing where they start, knowing where they end, their diameter, their length, etc., we can do many statistical characterizations. And much of this stuff is actually work of Andreas Grieser, my colleague. And you can, for example, get a fiber length distribution, you can get a fiber diameter distribution, you can get a fiber curvature distribution, and you can get an orientation distribution. For example, up here, you can get you can clearly see that the fibers are very much oriented in the XY plane here, due to these polar plots. They will show you this. And you can also get these kind of analysis on a bi-layer basis. And what you can also do, which I'm not covering here, is you can actually segment your structure by this property. So by these properties. So for example, you can segment your fiber structure by a certain length of fiber. So basically you can make a cut here, and you can visualize all the fibers that are shorter than this in red and all the other fibers in green, for example. And I think you can do this for most of these properties. So you can get a thorough understanding of your structure and how these properties of your fibers are distributed within the structure. Mm-hmm. So there's a lot of potential analysis that you can do. And possibly also do yourself if you want. You can actually get this GUT information from Geodict easily with GeoPython, and trace and do any analysis along the fibers that you want, because this is a really straightforward representation of the fibers. Now the next step, and in the next step, I want to explain how this first step, extracting the center lines, works in the FiberFind AI workflow. So again, this is the problem formulation just for the first step. We start out with a segmented image. Segmented means two material phases. We have the void space and the solid phase. So the void space here is transparent with a white background, and the solid phase is red. And now the question is, how do we get from the left image to the right image, the image where those center lines have been marked in green in an additional material phase? The solution that we use is a supervised deep learning approach. So let's, for the moment, assume we have many pairs of these structures. So we have segmented structures on the left-hand side, and we have matching. So it must be basically the same structure on the right-hand side with the center lines marked. Assume we have that already, and I will explain how to obtain that later. Now what we do is we train a deep neural network, an image-to-image model, which takes structures of the left nature here. Let's call it X as an input to the function, and produces these segmented structures with the center lines marked Y on the right-hand side. Clearly, this is just a function. You put an image of this kind into that function, and you obtain an image like the right one. And how this works is in deep learning is we train the network to so assuming we have a pair XY of images where we know the Y image is the correctly labeled X image, basically. Then we put our image X into the current neural network, maybe into the uninitialized neural network. We obtain a prediction of the neural network, an output, and then we compare this prediction with the ground truth that we already know, the Y, that we already know for this structure X. And we compute the error of that. Then we compute the gradients of that error, which shows us a first order approximation of a direction where we need to change the neural network in order to reduce that error. So we then apply this error reduction. We modify the weights of the neural network, the multiplicative and additive weights of the neural network, in order to ideally reduce that error in the next iteration, and we repeat that process until the result is good enough. And ideally, then it would, at least for all the image pairs that we have, map each x to the expected y image. But again, this typically requires multiple passes over the example data. So what we use in Geodict mainly is the so-called UNet architecture, which is pretty well known. I think it's by far the most famous image-to-image model. And this model, it takes a 3D image of a fixed resolution. I'm going to talk about that on the next slide, and outputs an output image of a smaller, also fixed resolution, fixed for a certain configuration of the network, which stays fixed during the whole process. So what this basically does, it uses convolution to reduce the input image in spatial resolution, but another dimension, a feature dimension, is added, which contains a rich representation of the image content, basically. And this is what happens on the way down the network here. You see it starts with a certain input image, which is this whole gray cube. Let's ignore the black one here for the moment. The whole gray cube is taken as an input. Here it's 52 by 52 by 52. Then some convolutions happen which slightly reduce the resolution, but the main point is that it's about halved going down here, the resolution. Again, something similar happens here. Then again, resolution is roughly halved. And then down here we have an image which is only 8 cubed in spatial resolution, but has a very rich representation of 64 feature values for each of these voxels. And then on the other hand side of the network, then this image is upscaled again with learned deconvolutions in order to obtain the result image. So basically it starts with this rich representation, and again it reduces the feature dimension again and increases the spatial dimension. And we don't end up with an image the same size of the input image, but with a smaller output image, which is centered in the center of that input image. But this image that results will then contain the center lines that we're looking for. Additionally, and that was the great invention with the UNet, is that we have these shortcut connections here, and so the whole architecture would also work without these shortcut connections. But this, as I understand, was a scientific breakthrough. These shortcut connections allow for a better localization of local features, because they give the network some of the raw data from the other side to look at in order to do to perform its decisions. Note here that you can also use, and I mentioned yesterday that we're using PyTorch now. We used to use TensorFlow, we use PyTorch now. But in Geodict 2024, you can then, if you want, also use your own architectures there. You can maybe download something from GitHub and plug that into Geodict, assuming that it works on 3D. So many implementations that you will find in UNet are by default still 2D, I suppose, but there are more and more 3D implementations coming up. So if you find an alternative that you believe that might work better, you can plug it into Geodict. So again, as I mentioned earlier, we still have the problem that the UNet takes a fixed size input, and not only is this input very not only our typical inputs much larger than this, but they also vary in size. So what we do to process, and this is of course part of the original UNet formulation. What we do in order to process these large images is we use a sliding window approach. So what you can see here in the first step, assuming we have our input image here in the background, we basically place our input window in the very upper left corner. So basically at corner 0, 0, 0 up here, and we grab all these 52 by 52 by 52 voxels here, feed that into the neural network, and the network will deliver us an output for only this smaller window in the center of that input window. But now what we can do in the next step, we can shift our input window and apply the same formulation again and obtain an output for the next output window. And of course, in order to first cover the whole input structure and to be efficient, of course, the amount that we shift will be the width of this output window. So we shift it exactly by the width of this output window. So we get a perfect tiling basically of our structure, and we get a result for every voxel. But as you might have seen, excluding in this image, excluding the border voxels here, because we cannot place this corner here because we don't have inputs for this border. So what we do for this purpose is we assume the image is mirrored at the very border. This typically works relatively well, but if you see artifacts that are happening at the very borders, at the very extremes of the domain, of the output domain, like x towards 0 or x towards n, all the boundary domains, that might explain it, because there's no real information. We are assuming a mirroring of the structure, so the outputs at the very boundary cannot be expected to be as good as the ones for the inside. Okay. Now there's one major question remaining, and that is how to obtain our training data. So how to obtain our X and Y image pairs. Of course, we might already have many segmented CT scans of our materials that we want to analyze, which are characteristic for our materials. And clearly, those could be used as inputs for our training, because the inputs are just segmented images. But the problem is, for those images, we don't know the corresponding output images. The corresponding means the very same image with the center line marked. And because it's 3D data, in almost all cases, manual labeling would be considered too much work for this. Now, the solution that we came up with is using synthetic training data. And this is because Geodict has powerful structure generators, as you know, for many types of materials. For example, fiber geo, paper geo, grain geo, weave geo, foam geo, grid geo, pleat geo, etc., and also GeoApps. And of course, for these generated structures, as I mentioned earlier, we already know the GID information, and this, of course, implies that we can trivially mark this center line. Essentially, what we do is basically we take the analytical fiber, we make a synthetic fiber which has a diameter of, I think, square root of 3 or something in a green color, and render that on top of the original structure. That's what we do. When we have the analytical representation, the gut information, it's basically trivial with Geodict to do. And that's what we're doing in Geodict AI. If you are training for fibers, if you're training for another application, I will show you later how that works. So the general idea, before we go into the break, is then we create a digital statistical twin of the material or family of materials that we're trying to analyze. Then we generate several random variations of this material in order to, so we have basically a distribution of materials which covers the materials that we expect to analyze. And when we have these pairs of images, X, Y pairs, basically, we can then train a neural network to map X to Y and therefore extract the center lines from these training structures. And finally, we can then take this neural network and apply it to CT scans of our real materials, and of course, analyze the statistics and characterize our materials. So the next part is about the digital statistical twin. What is a digital statistical twin, and how can we obtain a digital statistical twin of the family of structures that we want to characterize? So the materials we are considering here, at least, the fiber structures, the nonwovens, are inherently stochastic. So that means for two different material samples, the fibers will never be in the same location. But they do follow a certain statistical distribution, for example, based on the machine parameters of our production. And FiberGeo generates structures somewhat in the same way. The outputs are generated stochastically. You get a different structure each time. So each time you press on the run button in FiberGeo, as you might know, you get a different structure. But the distribution of this structure, for example, the fiber diameter distribution, the orientation distribution, etc., and the porosity or solid volume percentage is controlled by the input parameters that you enter into the dialog of FiberGeo. So here the goal is not to exactly reproduce a material sample, reproduce an analytical representation of our CT scan, but to find parameters of our structure generators, and in this case FiberGeo, which generate similar material samples. And what is a similar material sample depends, of course, on your demands. with respect to these structures. And this set of generator parameters, or rather this distribution of materials, is what we call a statistical digital twin. Not a concrete sample, but a distribution basically of samples. Now, how do we obtain a statistical digital twin for our material sample? We can see here that on the left-hand side, again, we have our segmented micro-CT scan, and on the right-hand side, we have the digital twin, or rather one instance of the digital twin, one generation result of FiberGeo. Now, the idea is that we can tune the FiberGeo parameters until we obtain a structure which is similar with regards to the characteristics that you care about to the real scan. And the geodetic analysis modules can help us here. They enable us to measure and compare the properties such as the fiber diameters, orientation distribution, curliness, pore size distribution, cloudiness, etc. And this in turn allows us to measure how close we are with our digital twin to the real material and to dial in the parameters. So this is basically a half automatic approach. Specifically for nonwovens, on the other hand, we now have the nonwoven digital twin app, which can generate digital twins pretty much automatically. Here we take the FiberFind results of a micro-CT scan and implement an automatic optimization loop which finds those parameters which are not directly computed by FiberFind, not by trial and error, but by the guided optimization approach. And for details, please see the talk by my colleague Andreas Grieser. And you can see here that the material that was scanned was closely matched in both flow permeability and also the fiber curvature distribution. The histogram was matched pretty well. So specifically for nonwovens, this is basically a shortcut that you can take. Now, how do we create the training data once we have our digital statistical twin? What we need to do for this purpose is to create a GeoPython macro. Once we have that GeoPython macro, Geodict AI can then automate the training data generation. But first, we need a GeoPython macro, which, when executed, will generate a single structure. So assume we have found a digital twin. We have run FiberGeo several times. We have analyzed this, and now we find that our last generated structure very closely matches our material. Then we can open the session macro dialog, which you can see on the right-hand side here in Geodict. You can just unfold this from the right-hand side of the user interface. And then you can scroll through all the commands that you have executed in this Geodict session. And then basically the point would be to find the latest, the last structure generation command. In this case, it's FiberGeo create. Select that, click this down arrow here, and you will then have you can then prepare a custom macro which contains this structure generation command alone. Then you can click the save button and you can save this macro as a Python file, just a GeoPython macro. Now we have one problem. We have this macro, as I said earlier, we need to generate several example structures. The problem is that within this macro, the random seed which defines the instance of a structure that was generated in FiberGeo is also stored in this macro. So in contrast to clicking the run button several times in the FiberGeo user interface, if you run this macro several times, you will get the very same structure each time. Because what happens behind the hood if you click the run button in FiberGeo is that we are actually incrementing the random seed in the user interface every time for you. So it is basically similar as going into the edit dialog of FiberGeo, changing the random seed, which you can enter there, and then clicking run again. But we do that for you, so you get a fresh structure every time. But this does not happen if you record it as a macro. This macro records the complete command, including the random seed. In this case, this was 42. So every time you run this, you get the same structure. Because of this, we now need to parameterize this structure generation macro. That means we add parameters or variables. And the very least that we need to do, and Geodict AI requires that in order to avoid this kind of error that I mentioned, is for the macro to have a GD seed parameter. It has to have that name. And when Geodict AI later generates training structures, this parameter is then automatically varied to make sure that every invocation of that macro produces a different structure. And at this point, if we need to cover If you need to, depending on the range of materials that we want to cover, we can also introduce any number of additional parameters. Say we have structures where we always have a constant diameter, but we have materials where the diameter varies from one sample to the other. Then we could introduce a fiber diameter parameter to our macro, and I will show you how to do this in the next slides, which allows us to randomly vary this parameter as well, to include basically to include a range of materials in our training distribution. And you can change, of course, you can change any parameter that you can change in FiberGeo, for example. So fiber diameter, orientation distribution, even the cross section. You could have hollow fibers, you could have elliptical fibers, and a mixture of both, or you can vary the solid volume percentage or porosity, or for example the binder volume. If there's binder between the fibers, you could also vary that. For that purpose, of course, you would need to generate a structure, then add binder, so you would have two commands in your macro. But it doesn't matter. You can add a parameter and introduce it to the add binder functionality. So now that just to show a synthetic example of structure variation, I have introduced I have a macro, and I've introduced two variables, one for the solid volume percentage in %, and for one for the fiber diameter in microns. And I'm just showing two different instances that could happen if this range of values was within the specified range. So here we have a 3% solid volume percentage and a fiber diameter of 8 microns. And here we have an 8% solid volume percentage and a fiber diameter of 15 microns. So just as an example. Okay, so now how to add these parameters to the macro as the next step. So again, we need to have a GDseed parameter, which identifies the instance, the stochastic instance of our structure that we want. And we can add any other parameters. I've shown here a parameter for solid volume percentage and one for fiber diameter. And now let's take our recorded macro and add these parameters. So in the macro, there should already be a variables block commented out at the very top of the macro. And you can change it like this. You can add these variable blocks here. The GDseed variable of an integer type. You can specify a default, but you don't have to. Solid volume percentage as a double value. Again, the built-in default doesn't matter that much in this case. In the check, you can specify minimum and maximum value. What this does, if it's present, is it defines the minimum maximum value that you can specify in the training data generation later. So you could basically there you want to specify the very limits of what you would ever expect to have to generate, the minimum and maximum, to make it easier to use in the user interface later. And then we have fiber diameter, again, a double variable with a unit micron, and that's mostly for documentation purposes. The unit that's here is, in the logic, it's ignored, it's just for documentation purposes. Now that we have added these variables, we now have a parametric macro. You can also, for example, in Geodict, in the execute macro dialog, you can also enter these variable values manually, run that macro, and it will generate the structure for you. Most of you might know that. Or you can also run a variation, which generates the whole set of structures depending on values. But at this point in time, we have added these as parameters, but we have not used them. So basically, they would be ignored right now, and it would still generate the very same structure. So what we need to do now, the next step is take these parameters and actually use them in the Geodict commands that were recorded within the macro. For example, the GDseed variable we would put into the random seed key here of the FiberGeo call. Fiber diameter is the value of this constant diameter distribution, also within the FiberGeo parameters, times 1e minus 6, because I want to be able to specify the diameter in microns, and within Geodict, within the commands, it's usually all SI units. So this expects meters. I want to be able to enter microns as the variable value, so I multiply by 1e minus 6. And then, last but not least, the solid volume percentage, which is specified here. So basically, you go into your macro, you find this entry random seed. There you will find whatever number was recorded earlier and replace all these numbers here. This goes for all the 3 numbers. Replace it by the variable name. Yeah, and actually we cover this in much detail in our GeoPython tutorial. So we have both a basic and an advanced GeoPython tutorial, and parameterizing macros not with a purpose for geodetic AI, but for automation in general, for running automated studies, for example, running simulations over many files or things like that. The GeoPython tutorials will explain in great detail how you can do that. And you can use that technique here. Now, that was already the worst part. Now, what we can do is the next step in geodetic AI. And by the way this talk is structured is mostly going through all the submenu entries that you will find in geodetic AI from top to bottom. So basically, the workflow is you go through all these submodules, and then you have your trained neural network more or less. So the next entry in that menu is designer. It's called design of experiments. Now we have our macro ready, and design of experiments will now allow us to explore our parameter space and generate basically a study of parameter variations, which then later will become the actual training structures. But first of all, we're talking about a table of values. So in this dialog, you specify the macro that you have created. You can specify a starting value for GDseed. If you're only doing a single training run, you can just leave that as the default. And importantly, you can specify a range for each of the other variables that you have defined. For example, for solid volume percentage here, I have specified a range between 3 and 8%. For the fiber diameter, I've specified a range between 8 and 15 micron. And then there's also an option how the variation algorithm should work. Because we have observed that, of course, intuitively, we chose to pick numbers randomly. So pseudo-randomly, of course. But we observed that if you look at this image on the lower left corner, assuming we have a two-dimensional parameter space, so we have two variables, one on the x and one on the y. Let's say that solid volume percentage and fiber diameters. You might get, especially with a low sample count, with a low number of structures, you might get a non-uniform covering of your parameter space. You can see that there are clearly voids here and that there are clearly strong clusterings of samples as well. And there's another deterministic approach, which is called Sobol algorithm, which will actually produce a much nicer, basically, tessellation or covering of your parameter space, which you can see here. You can look that up on Wikipedia for details about how this works, but we always recommend to use the Sobol algorithm usually. Now, last but not least, what you have to specify is the number of training structures to generate for the training and the number of test structures. So the training structures are the ones which are actually going to be used during training the neural network. So this is basically what the training process sees. And the test structures are basically a holdout set that is not going to be analyzed by the training. So the test structures that are generated, basically you can use them later to test if the network that you have trained on your training structures generalizes to those test structures. So they are pulled from the same distribution, but they are never considered in training. So it cannot learn directly from these structures. So for very first tests, for really testing of something works, actually you can use a single structure for training. For testing, you can say have one training structure, one test structure, and just see what happens. Because I mean, everyone knows that for deep learning, you need a lot of samples, right? But in this case, one structure would not be considered one sample because we have the sliding window approach. Actually, each input window, each window is one sample in this training process. And as you know, 3D structure, if you slide a window across that, a relatively small window, you will get a lot of windows just out of one structure. So that's already a lot of samples within one structure. So for testing purposes, one structure is enough for testing if it works. Yeah. Of course, it also depends on how complex your parameter space is, yeah, that you want to cover with your structures. If you want to cover it uniformly and you have many parameters or large range, then you might need to have more structures. But I believe we never used more than 100 in our internal training. So again, the design of experiments part here is only about generating table values and also analyzing them to make sure that you cover your distribution correctly. So there are no structures being generated at this point, but instead we obtain a table here of actually values parameter values. So you basically get two results. You get a GDR result file from design of experiments, and within that result file, you will find for each variable you will find a plot which shows you how the value distribution of that variable looks. So you can see here that it at these, I don't know if this was actually for 100 structures. Anyways, you can see here that it has achieved a pretty uniform distribution of these two variables, which might have not been the case if we had chosen random before. You can actually see the difference if you choose random and snowball, if you only generate small number of structures especially. And also, the most important part is it produces a table in CSV format. And as you might know, CSV file, you can usually just in Windows, you can just double click and open it in Excel. And in that CSV file, you will see the actual instances that it has generated. So for each, basically, you get the title, and then each row below that corresponds to one structure that is about to be generated. And it's classified between train and test structures. Also, actually, this is 10 train structures and probably one test structure here. It says train or test here in the first column, signifying if this is going to be a train or test structure. Here is the random seed for that specific structure. You can see, importantly, that the seed increments above the border between train and test. So this test structure is going to be different from all the other training structures up here because it has a different random seed. And we have the SVP value, the solid volume percentage, and the fiber diameter for that structure. So that basically just generates this table. You can look at the values, you can look at the distribution, you can also plot these values in Excel, and you can also modify them in Excel. Or you can also generate a file like this from scratch in Excel in order to match your distribution as you want to fit it. Now, assuming we're happy with that CSV file after editing it, for example, or just looking at it, next we can use the create training data function, which is the next item in the drop-down menu in Geodict AI. So for this, we need to specify the very same macro that we had before. We need to specify an empty output directory for the training and actually the test structures. Where the structures end up that are being generated. And we need to select the sample CSV file that was generated in the previous step. And then there's a fourth option here, which I'll explain on the next slide, which is the object type that we are working with. So in object type or post-processing here, there's currently two options. You can choose either fibers, center lines, which we will do here, obviously, or you can choose material phases. So if you select center lines, then it will assume that your macro contains commands which generate a fiber structure, meaning that when you run the macro, say you run it manually, you have a fiber structure in Geodict with GID information, which is the normal case if you just run FiberGeo. So it assumes it will generate a fiber structure and basically do nothing else. Then this create training data function will, from that fiber structure, automatically generate the X and Ys that we need for the neural network training. And those are actually called input GDT and output GDT in our case. So basically, it will run your macro and it will obtain this with a certain variable value, and it will obtain this input GDT. And then it will add to this structure basically the center lines, which it can do because it knows the analytical information about the fibers, and save that as output GDT. And then that's basically the pair of structures that we need for our neural network training. Now, the other option is called material phases. So this is meant for taking a binary image again, but segmenting a material phase. So assume you have a micro CT scan of a fiber structure which has binder content in it, and you cannot, by gray value alone or by any other traditional segmentation methods, distinguish between the fibers and the binder material. So you have a structure like here on the left-hand side. What you can do then is you can generate synthetic structures with FiberGeo again, use the add binder functionality to add the binder in a different color, and use that as training data for Geodict AI. So in this case, you have to your macro gets a little bit more complicated. You have to go and generate the fiber structure, add binder. You can record both of these. Then save that structure as output GDT. Again, you can also record that just as commands in the session macro. Then you reassign the green part to red, so it becomes indistinguishable from the fibers, and save that as input GDT. So that's what you have to do within the macro. And then you have to select material phases up here. And in this case, the training works a little bit different. It does not do any center line extraction or anything like that. It will basically take your input as is. So it will assume that it has to map images of this nature to images of this nature. So basically just mark a subset of voxels as green without any post-processing like tracing center lines. I will have a word about that later as well. So now if we run create training data, we get a set of structures which is visualized here. Again, these are the G32 labels of the structures that have been generated, or a couple of structures. And what it will do, it will go through the sample CSV file. And for each of the value rows, so excluding the title, of course, it will generate a structure in a separate subfolder. So we have a train subfolder where the training structures will end up. So we have a train subfolder in each train. In the train subfolder, you get a subfolder for each structure. And the same goes for test. And it will also apply the selected post-processing. For example, for fibers, it will again save the structure as input GDT, add the center lines to the structure, and save that as output GDT. So you get your XY pair for training. So this looks like this then. So assuming here the top folder that we cannot see here is the output folder that we have specified. Then within that folder, we have a folder train, which contains the training structures. And then we have one instance of these training structures, the number 42, would be the seed in this case, named by the seed, which contains the structure. And it not only contains the structure, but it contains everything that the macro happens to produce when it runs. But the important part here is that we will end up with an input GDT, which corresponds to the left-hand image here, and an output GDT, which corresponds to the right-hand image here, again, in separate folders. And yeah, exactly as it says here. And these are then the image pairs that we use for training. So now, as you have seen the folder structure and how it can be, the training data, the synthetic training data can be generated. Of course, if you have other means of generating this kind of training data, you can also do that. So for example, if you could somehow mark a material phase of your material using something that shows up as a contrast in a microCT for an experiment. So basically you end up with a material which looks like your production material, but you happen to be able to add a contrast agent to one of your phases, maybe to the binder material, and you have, even if you have only a small number of these images where you can easily segment with traditional means these three material phases, void, fibers, binder, say, then you can construct basically construct a folder structure like this and use that as training data. Of course, if you can do that, that would be much better than the synthetic data, because it should ideally fit your actual material perfectly, if possible. So if you can come up with any way to do this for some sample structures, and maybe a handful of structures or samples would even be enough, that would probably be the very best option to go. So now we have we basically have our folder with our training and testing structure, and now we need to train our neural network. And let me see. And that would actually be the next option in Geodict AI. So this is a rather large dialog, but I will go through it part by part. So the training options here, that's the dialog that you see here, has basically 4 sections. You have up here, let me activate the pointer again. So up here you have the GDR result file name and the description text. And the description text is it's basically meant to inform the user of your neural network for which kind of structures this neural network was trained. So essentially, most importantly, you would, for example, put in what the fiber diameter range, the fiber cross section that you would expect this network to work for would be. So if you train several networks, that maybe your colleague can then decide which network to pick based on this description text. But this is not a functional thing. It's just a text that is stored with the network. Then we have, and I will talk about this in detail in the next slides, we have the neural network parameters here on the left-hand side. We have the GPU setup here, and we have the input data configuration in this lower hand part. So note here that the training, I said earlier that training usually requires multiple passes over the data. And one such pass is called an epoch in neural network training terminology. And you can somewhat compare that to the iteration of a solver. One epoch, again, is one pass over a fixed amount of data. After each epoch, you get an evaluation or an estimation of the performance of the neural network right now. So it could be comparable to, as I said, an iteration of a solver, which then gives you the residual, showing you an estimate of how close you are to the intended solution. So that can be compared. So first of all, let's start with the model parameters. Here, this is one crop of that dialog that we saw the slide before. So here you can choose a neural network model. Right now, when Geodict S shipped, you can only select UNet there. We might add models in the future, but if you have custom models, they will also appear in this drop-down menu up here. Then you can enter a maximum number of epochs. And at this point in time, I would suggest always putting a large number here. 100 is often large enough. You can put 1000 to be safe. And this is the number of epochs that it will run the training for before it automatically stops. We suggest putting this at a large number, starting the training, and as I will show you later, just observing the training process. And if it's obviously converging, then you can stop manually. So I wouldn't worry too much about this max number of epochs. Just put a high number in right now. For the optimizer, we have two options. We have ADAM and SGD, stochastic gradient descent. ADAM is, I think, by far the most popular production optimizer being used right now. In some research papers, you will see SGD, which can have another 1 or 2% of performance in the end, but I believe at the cost of a larger number of iterations. So I believe for 99% of usages, you would just leave this at ADAM. And down here, you can also load a custom optimizer, which I believe was never actually used by anyone. But if you require this feature and you want to know how to do this, just let us know. So now there's an edit button next to the model, and the dialog that comes up then, that is dependent on the model. So within the model definition, you can specify variables that are so-called hyperparameters for your model. And the classical hyperparameters for the UNet, in this case, here again is here's the reference, by the way, for UNet, but you can also just Google UNet. I think it's the most popular, one of the most popular neural networks ever. There is the depth of the UNet here, and there is the number of features in the first layer, and the size of the convolutional kernel. So right off the bat, the size of the convolutional kernel, I believe, is also very often 3 in literature, and I believe you seldomly should change this to 5, and only 3 and 5 are the viable options in this case. The other parameters, though, you might want to change. And just for illustration purposes, let me just quickly go back to the UNet diagram. Here, the UNet again. The depth is the number of basically steps downwards that you have here. So I'm not sure if this is 2 or 3, but actually, if you increase the depth, you will get another layer here in the UNet. And the number of features is here, this 16 in this case, is the number of features extracted here. So both increasing the depth and increasing the number of features increases the complexity of the neural network. So it broadens basically the ability of configurations that it might be able to learn. But to obtain the same performance as a simpler network on a simple task, it probably needs more iterations and maybe more data. But in our case, because again, we have so many windows in the structure, the amount of data is usually not the problem. In many other applications it is, but because we're using synthetic data, you would assume that the amount of data is not the problem, but it might take longer. So, and especially for our case, because we're using 3D networks, it also increases the memory that you need. And the implication of that is that if you go to say a depth of 4 here, this I believe will not work on most GPUs that you can buy. So the limit is usually 3 here because we're using 3D. If you look at the literature, you might see depths of 5 or 2 or 6, but mostly then these are for 2D applications where you can go with a higher depth. So there's not many choices here for depth that are actually feasible. So it's usually 2 or 3 that you can experiment with. Again, increasing the depth increases the runtime, increases the length of an epoch, and it might at the same time increase the number of epochs that you need to do. So for experimentation purposes, I would say you should start out with the defaults, which are rather low, but still practical for many applications. So 2 and 16, and then you can try increasing the number of features if the network doesn't perform as well as you expect. And later, maybe try increasing the depth as well. Next, there's the GPU parameters. So here, as I said in my other talk yesterday, we now support multi-GPU training and inference. And if you have multiple GPUs, so this was recorded on my laptop as a mobile GPU here. If you have multiple GPUs, you will actually see a list here with checkboxes where you can select the subset of GPUs to use. Say if you have 4 identical GPUs, you can select them all and it will run in parallel on all of these GPUs. Note that an NVIDIA GPU right now is necessary because I believe PyTorch does not yet run well on AMD hardware, and running on CPU is totally out of the question because it would be way too slow. Inference, so applying a neural network, is still in the ballpark of what could be tolerable on a CPU would probably need a factor 10 runtime compared to a GPU, but training, I believe, is not feasible on CPU. And on AMD, it's not really supported, so you basically need an NVIDIA GPU. But the good news is that often a consumer GPU in the, say, 1,000 euro range is enough, even for training, for many applications. So you can start with a workstation hardware, basically. The batch size, then, I would suggest setting as high as possible. The batch size is the number of these input windows that it will batch together and process at the same time on the GPU. And it's basically the amount that you can set there is a function of the memory on your GPU. So I would increase it because a batch size of 1 has a lot of overhead, because then it takes a single window, has to upload it to the GPU, wait till the upload is done, the GPU has to calculate, download it, wait for it to be done. So that gets a lot of communication overhead between the CPU and GPU. And the higher you can set the batch size, the lower this overhead becomes. So I would suggest increasing it until you get an error out of memory error message and then dialing it down a bit. So yeah, if you change the topology of the network, if you change these parameters down here, the amount of memory changes. So you will then have to possibly change the batch size that you can run. So next we have the input data setup. Here you select the input data set folder is just the folder which you have selected as your output folder in a create training data step. So basically the folder which contains the train test, and in there are the structures. This top folder basically you select here. And then there is here the train test split factor. Unfortunately, we chose the same name here, which is unfortunate because, so this is not referring to the test structures earlier, but it will, as I said, the training will only consider the structures in the train folder. But during training, it will take 90% of those windows, basically, for training, and 10%, if it's set up to 0.9, for validation, for checking the convergence, for checking the validation loss in each epoch. So you basically, all your structures are split in 3 ways. First of all, you have the train structures, the test structures, then the training runs on the training structures, and those are, again, dynamically at runtime split into 90-10 in this case, for training and for checking the convergence. And then there's the downsampling factor, which defines the size of an epoch. So downsampling factor, assume you have that sliding window. You apply that window to each of your training structures. You put it at every location that you could put it. So it's still within the structure. You get many windows, and that times the number of structures that you have. So you have 100,000, 1 million windows, for example. And Now, of course, doing a whole pass over that data might take too long. So if you want feedback how your network is converging, you don't want to wait until it has done might not want to wait until it has done a pass over the whole data. So this downsampling factor then defines what percentage, what fraction of your whole data you are using in each epoch. So this defines the length of an epoch. Within each epoch, you get basically a snapshot of the neural network that you can use later, a GNN file which contains the trained neural network. And you also get the evaluation of the convergence. So you get one data point on your convergence graph. So you might want to choose that in a range, and you have to just try it out. Where one epoch is maybe 30 to 60 minutes in length. Also because you don't want to make it too short, because again, there's more overhead then, and you always get a snapshot of your GNN. It might actually fill up your hard drive depending on the size of the network. So I would say experiment with a low number, increase it until you are in the ballpark of 30 to 60 minutes per epoch. Then you get regular updates about your training progression, and you don't fill up your hard drive. Next, we have the window size. And this is basically, as I showed earlier, the size of the input windows. Okay, next is the window size. The window size is the input window size. So that's basically the context that the neural network sees that it can use to decide how to label the voxels in the smaller output window that's centered within that input window. And so you have to consider that the window size has to be chosen depending on your structure. It needs to be able to. You have to imagine that this is kind of a peephole that the neural network sees, and that's all it sees. It only sees that input window, and based on that window alone, it has to decide how to mark these voxels in the center of the window. And if you imagine that you have fibers, say, that are much bigger than your input window, then the input window might see all red voxels, just red voxels. And then, of course, it cannot decide where to put the center line because it has no idea where inside the fiber it is. So, for example, for fibers, we suggest, and that's based on our experimentation, we would suggest making the window size at least 2 times as large as the fiber diameter. And another thing, for example, if you have fibers with binder and you have, say, a lot of binder, and you have cross sections where fibers meet and you have binder, which forms a large blob, then intuitively, you would, if you want to segment the binder, say, you would want the window to be large enough to see the context of the fibers, which are not covered by binder, coming into this intersection from the outside. So it would be able to basically predict the trajectory of these fibers in order to make sense of this blob in the middle. If it only sees a smaller window, it might just see a red window completely filled with red voxels. It has no idea what could be binder, what could be fiber. So, and for for anisotropic structures like the nonwoven that we saw, which are oriented in the plane, it might also make sense to make the window smaller in Z, because again, this also needs memory. So the window should be as small as feasible, because most of the action happens in the XY plane. Yeah? So it might make sense to make Z smaller, and potentially as a trade-off, then you can make X and Y larger. Then there's also the augmentation factor, where the data is mirrored and rotated. You can select 3 different options there. So it will take each window, and it will also consider like the mirrored version of that window, where of course the input and the output has been identically mirrored, and will also consider that in the data. And you can, if you consider all rotations and all 90-degree multiple rotations and all mirrorings that you can do, you get to up to factor 48. So, for example, for synthetic data, I would always suggest generating enough data instead. But if you have, for example, manually labeled data, or for example, done it with like a marker process or something, then of course the data becomes much more valuable. And then you might really want to consider using this data augmentation feature to make the most use, to blow up your data basically. Because a neural network, in this case, a convolutional neural network like this, does not consider like a rotated sample the same as the non-rotated sample. It has to see the same sample in both orientations intuitively to learn both configurations independently. So now in the Geodetic console, once you run the training, you will see a regular output here for each epoch. It says here that it has saved if you open the console, and you can do that from the progress bar, you can open the console there as well. It has saved one snapshot, epoch105.gnn, and that you can find in the result folder of the training. And actually, you can take that file and try it out, possibly on a different machine because your GPU might be occupied, but you can take that file, go to another machine and try it out on your data while the training is still running. But this GPU shouldn't be used for anything else at that moment. And it will also tell you if it has found a better loss. So the loss is basically the equivalent of the residual in a solver. The lower the loss, the better the network is or estimates to be. So what it does, apart from writing snapshots every time, and also while assuming that the convergence gets better all the time, it will also take the best model at any point in time and copy that to best model GNN as well. So usually what you would do after the training, you pick that best model GNN because that numerically has might have a bit better performance than the very last snapshot that you have. So yeah, again, I would suggest not specifying a fixed number of epochs, but looking at the convergence graph. So this is the plot of that number that you will see in the console. That's the validation loss. That's like the 10% holdout of the training data. So it tests the performance on that 10% holdout set and gives you that loss number. And you can see here that it converges, that it plateaus here. And the idea then is that you look at that graph, and once you see it plateau, you can click the stop button. It will then finish the current epoch and stop the training. Also for this purpose, the epoch shouldn't be too long because then you might have to wait a couple of hours when you click stop. And yeah, so this is actually the important number. The other number is the loss on the training data itself. That's not being plotted because that's actually the number that you should look at. So we recently, okay, for those in the know, we recently added the IOU score, intersection over unit over union, which is a popular metric for characterizing a classifier, and that is also being plotted and output in the results. So now, last but not least, we can, of course, apply the network to our material sample, and we obtain a segmentation of our individual fibers. Now, last but not least, if you want to do material phase segmentation, and I already mentioned most of this actually. So here in material phase segmentation, we don't produce center lines, but the result is just the output of the network. By the way, this is being thresholded, so the network actually outputs a value between 0 and 1 for each voxel, and we just usually can change that, but usually we say the cutoff is at 0.5. So if the network predicts a number larger than 0.5, the voxel becomes green. If it's smaller than 0.5, the voxel stays red, basically. And for material phase segmentation, it's easier because conceptually easier because there's no post-processing. Whatever the network outputs is thresholded, and that's your resulting image. And then last thing that you can do, you can also use this to train a neural network to enhance grayscale images now. So I talked about this, I think, in my other talk. So if you have grayscale image pairs, for example, with a short exposure and a long exposure, taken with the same projections, with the same sample, same machine, so they are perfectly aligned. You can take these samples and actually produce a training data folder with a structure that I mentioned before, but you won't have input GDT and output GDT, but input GRW and output GRW, which are geodetic grayscale images. And it will automatically, you can run the training in the same way, it will automatically detect which it is, and it will run a different loss metric, different backend, in order to work on grayscale images. And then you can apply this in, for example, in import GeoWall. Once you have trained this network, you can load a low quality CT image, apply that trained neural network, and get a high quality image out. So in conclusion, I've shown you how you can use geodetic AI to train your own neural networks optimized for your task. There it is, the variable editor, Aaron. That's something that again my colleague Andreas Grieser is working on. That would be a feature, possibly in 2025, I suppose, where you can just take your session macro and open it in a graphical user interface and add your variables and say which parameter of which command you want to replace without ever opening the macro in an editor. But right now, unfortunately, you still have to do that. And again, I want to refer to our GeoPython tutorials, where a large part of these tutorials are about parameterizing macros. So exactly what you need for this.